Snowboarding. So Zoe is snowboard racing in the mountains. Here we have our mountain and Zoe and snowboarding and racing. The finish line. Halfway there. But this is a physics paper, right? Mechanics. And so we're given a distance time graph to show Zoe's progress through the race. So before we even look at the first question, let's just see what's going on here. So you're racing. Okay, so you'd start at 0 meters. That makes sense, right? That's a start line. That's where you start the clock from. And then once you've completed the race, you'd stop, right? You'd finish. You might fall over at the end out of excitement because you won. But so that's what this section is representing. So Zoe has finished the race, and we can see the total distance of the race as well, right? So that's what, 2.3 kilometers, 2,300 meters. So Zoe traveled a distance of 2,300 meters at this time here, 240 seconds. And so just from that, we can reasonably estimate that Zoe finished the race, right? That's what this flat section represents. We'll make that assumption. And it took her, 4 minutes, 240 seconds to travel that distance of 2,300 meters. All right, and that's a distance time graph, so that tells us she's at that distance for this time. So a flat line means she's not moving. However, throughout the race, she would be accelerating, decelerating, or traveling at a constant speed. And on a distance time graph, a constant gradient, in other words, this this constant gradient here in section B. Oh, that's not where section B is either. In section B, constant gradient on a distance time graph represents a constant speed. Constant speed. So in section B, Zoe is traveling at a constant speed. However, in order to get moving at the start, Zoe would have to accelerate. That's why it's curved upwards like that. And then at the end, she might be braking. Maybe the finish line is here actually. And then in section C, she's decelerating. That's why it's curved downwards. So with those features in mind, we can answer the first question to describe Zoe's motion. So in section A, on this distance time graph, since it's curved upwards, we say Zoe is accelerating. In section B, since it's a constant gradient, right, it's not curved, but it's not flat, right, it has a non-zero gradient, we say Zoe is traveling at a constant speed. In section C, it's curved downwards. So on a distance time graph, we say that is decelerating. So decelerating or slowing down. Or accelerating negatively, right? A negative acceleration, that's fine too. And in section D, a horizontal or a flat line, that is a constant gradient, right? So technically she is traveling at a constant speed. However, it's a speed of 0. So we say stationary or just stopped, not moving. Or if you want to be technical, constant speed of 0 meters per second, right? That is a constant speed, but it's, 0. And so that's describing Zoe's movement throughout the race. All right, question B. How long does Zoe's total journey take? Okay. So the journey is the distance traveled, right? The total distance traveled. So looking at section D over here, she hasn't gained any more distance, right? She hasn't gone further. So really, Zoe's journey ends at this point right here, right at the boundary of section C and D. Sure, she's waiting around in section D, but her journey's over, right? She's finished the race. And so the time it took to get there, if we drop down on this dashed line, we looked at before, was 240 seconds, right? So each grid line is 10 seconds. Make sure you double check the scale. So 240 seconds. Or divide it by 60 to get 4 minutes. But we're in physics, so let's go with the SI units, which is seconds. Question C, calculate the speed of Zoe in section B. Section B, we know on a distance time graph that speed is equal to the change in distance over the change in time. And for a constant gradient, we can work out what that speed is. However, if it asked us what is the speed in section A, we'd need some calculus, right? Because her speed is actually changing, so that's not a very good question. But we're in section B, and her speed is the change in distance. So that's up to here. So the change in distance over the change in time. So how long it took to travel that distance. Awesome. So we just need to be a little bit careful when we find the change in distance. We find that distance between these 2 points. So that X and that X. Right, and we just account for the grid. So she starts at a distance of 300. Right there, and finishes at a distance of 2,200. So the change in distance will be 2,200 minus 300. And the change in time, she starts at 40 seconds and travels that distance at 220 seconds. So the change in time would be 220 minus 40. Right, so just to emphasize those points, just highlighting them, because this is the easy bit to mess up, counting the grid squares. So do take your time with the scale, label the points, double check it, triple check it, and then that gives us our equation for the speed, which we can then compute. Whoa. Okay, I lowered my resolution, and this is what we get. So I trust that you can use a calculator to compute this, and we get 10.55, and then our units for speed are meters per second. So you can write it like that, or meters over seconds. Both are correct. So that is her speed in section B. Pretty fast. So it must be quite a steep mountain. Question D. All right, there's a different race that is a bit longer, so 3,000 meters. And Zoe's averaged a speed of 5 meters per second, so she's gone slower. So maybe it's more slalom, like a more challenging race. And then we're asked to calculate the time it would take for her to finish the race. So she's got a distance of 3,000 meters, and she's traveling 5 meters each second. How many seconds does it take to finish the race? Right, and we can just use the formula for speed, distance, and time. And we're trying to find out the time. So we can rearrange this as time equals distance over velocity. And if you're not comfortable rearranging, there are the formula triangles, which is rearranging, but just a bit more visual. So if we're looking for time, we cover up time. So time equals, and then we're left with distance divided by velocity. So again, we're looking for time, we're using the speed, distance, time equation, and solving for time. Then substituting in what we know, distance of 3,000 meters, and a speed of 5 meters per second, which gives us 600 seconds. So a 10-minute race, so quite a bit longer. Question E. All right, so after the race, Zoe's like, okay, time to go home. And she's wearing snowshoes. We're given the area of one snowshoe as 0.15 meters squared compared to the surface area of one walking shoe. And we're given Zoe's weight as opposed to mass. And firstly, we need to calculate the pressure for a snowshoe or a walking shoe, and then just explain why wearing a snowshoe is better for Zoe and makes it easier to walk on the soft snow. So calculating the pressure, if you forget a formula, no stress, go back up to the top. We're given the formula, so the formula for pressure, so this P is pressure, this P is power. I know, physics is annoying like that. Yeah, how you remember that, that's up to you. They're both capital P in this case, but we're relating pressure to force and area. So before we get started, let's just write out that equation so we know. So for one snowshoe, we can calculate the pressure that Zoe exerts on the ground. So that pressure is equal to the force. Now, we're assuming that the only force acting downwards is Zoe's weight. It would be different if Zoe was lifting up her foot or pushing it down, right? Using her muscles to add additional force. We're just going to assume she's standing still. The only force acting down is her weight, which is 570 newtons, divided by the contact area of one snowshoe. Sometimes they'll try to trick you, right, and say 2 snowshoes or for Zoe, so then that's implied, but here they're being quite generous. And the snowshoe area is 0.15 meters squared, and if you compute that, you get 3,800. And now if you forget the units, you can just look at the formula here. So we had newtons over meters squared. So a valid unit for pressure is newtons per meter squared. But in level 1 physics, we use pascals. However, if you do forget, newtons per meter squared is still correct. So that's the pressure for one snowshoe. Now, do we expect the pressure for a walking shoe to be greater or less? Right, same force, smaller area. So if the area goes down, we'd expect the pressure to go up. So let's just verify that. Pressure equals the same force over a smaller area, 0.03, gives us a pressure of 19,000 pascals. So that's significantly greater. And now we need to explain this difference and why it's better or easier to walk on the snow in a snowshoe. Hopefully 2 snowshoes, but I guess if you just had one, it's still better than none. So let's look back to this formula. What's staying the same and what's changing? So Zoe's weight remains the same. So Zoe's or let's make it more general, right? Because it's not asking us specifically about Zoe. So we'd say weight force or weight remains the same. Full stop. Right, first sentence. In this example, it was 570 newtons, but if it was me, might be a bit more. Maybe not too much, just a bit. Yeah. Okay, a lot. Anyway, okay, what's changing? The area changes. Okay, so area of snowshoe is greater than the area of a walking shoe. Yep, makes sense. This means that the pressure exerted while wearing a snowshoe will be less than a walking shoe as, now here's the bit lots of students forget, as pressure is inversely proportional to area. What that means is as area goes up, pressure goes down. So there, whereas pressure and force are proportional, right? If the force goes up, right, like if you're heavier like me, the pressure goes up. However, for a constant force, if area goes up, pressure goes down, so we say they're inversely proportional. And so just to summarize this last one, we commented on what stayed the same, in this case the force, what changed between a snowshoe and a walking shoe, that was the area. We then wrote a concluding statement as to which one would be easier or harder to walk on the snow. Well, actually we missed that bit, didn't we? So we talked about the pressure, and then final concluding statement, just linking it back to the question, meaning it is easier to walk, oh, that's a funny walk, to walk on snow with a snowshoe, or while wearing snowshoes. However, they've just given us one snowshoe. All right, and then we've answered the question. So do just read the question again, make sure your last sentence is explicitly answering that, but the 3 points before that explored the physics relating pressure, force, and area. And so there we go. Good job.